Hi everybody, this is Dr. Niger with the Screencast for our thermochemistry unit. This one is going to focus on an experimental technique called calorimetry. All right, so calorimetry is an experimental technique that allows you to monitor the flow of energy, and that can be between objects or due to a reaction. All right, we are going to actually look at examples of each. All right, and calorimetry experiments can be simple. All right, for example, you could use a coffee cup, you could pour some water in and dissolve a solid in it, monitor the temperature, and that would be considered calorimetry. Other calorimetry experiments can be very complex. We have some reactions that don't run well in an aqueous environment, so you use something called a bomb calorimeter, which has basically a calorimeter inside of a calorimeter. All right, but in general, they're all going to follow the same steps. So they could be simple or complex, but at their root, they're all going to be looking at the same thing. So what does a calorimetry experiment look like? All right, so usually when I work calorimetry experiments, I draw a little picture. Now, this is not required, and as my students will tell you, I'm not an artist. All right, but usually the apparatus that we use is some sort of insulated cup. All right, it could be styrofoam cup seems to work the best. We use coffee cups all the time. All right, and in that, we tend to use a substance that has a pretty high specific heat. And one of the best substances for these types of experiments is water. All right, so we're going to put water in our cup, and then we're going to know the mass of that water. All right, we're going to measure its initial temperature, and then at the end of the experiment, we'll be looking at its final temperature. All right, that's going to give us the delta T for the water. All right, and then in addition, we need to know the specific heat of water. And since that's a physical property, that's something that we can easily look up. All right, so for this calorimetry experiment, we're monitoring the flow of energy from water's perspective. So we're monitoring from H2O's view, if you want to think of it that way. All right, and that's going to be an important thing to keep in mind because we're going to be talking about what the object or the reaction is doing, which means we need to know the flow of energy from water's perspective, but we're going to be changing the sign. All right, so this is an indirect observation. All right, and that energy that we're monitoring will either flow into the water or out of the water. And the direction of flow that we see based on that change in temperature is going to tell us what the reaction of the object is doing. All right, so we're going to use this information and we're going to be calculating the energy that water perceives, and then that is going to be used to determine the energy of the reaction or the energy moving from the object. All right, these two values are going to have the same numerical value. They'll have the same magnitude, but they will have different signs because the water, for example, if its temperature goes up, is absorbing energy. So that'll have a positive Q value, an endothermic process. But that means that that energy is actually moving from the reaction or the object. So the reaction or object is releasing that energy, which makes it exothermic. So we put a negative sign in front of that Q value. All right. As the temperature of the water changes, let's say it increases, that's going to tell us what the object or the reaction is doing. So if the temperature goes up, then our object or reaction is releasing, releasing energy. I'm going to run in that. All right. So we're going to be monitoring that temperature change of the water. And I'll talk a little bit more about that when we get to these problems. All right. So let's slide down. Let's look at this first problem. All right, a piece of metal with a mass of 59.047 grams was heated to 100 degrees Celsius. The hot metal was added to 100 mils of water at an initial temperature of 23.7 degrees Celsius. The metal and water reached an equilibrium temperature of 27.8 degrees Celsius. All right, so again, I like to draw little pictures. All right, so here's what I know. All right, I have water in my calorimeter, all right, and I have 100 milliliters. Now remember, the density of water is 1 gram per milliliter, all right? So that means if I know the volume, then I know the mass. So instead of 100 milliliters, I'm going to use the mass as 100 grams, all right? The water had an initial temperature of 23.7 degrees Celsius, and once the metal was added, we saw that temperature increase until we reached thermal equilibrium and saw a temperature of 27.8 degrees Celsius. So this piece of metal was dropped into our water, and we observed the temperature of H2O increase. So what that tells me is that energy is flowing from my piece of metal into the water as it absorbs that energy. Okay? Now, the first question is energy flowing into the water or out? So as I said, because the temperature of H2O increases, the energy is flowing into the water. If the temperature of water went down, then we would know that energy is flowing out of the water. So remember, the direction of the temperature change is going to be what tells us which way energy is flowing. All right, so the next question then is, well, how much energy is being transferred? So we're going to be looking for Q. All right, so I like to list out what I have. So we're going to be looking at it from water's perspective. So I have water, all right, and I don't know the energy that's flowing. All right, I do know the mass of my water sample. It's 100 grams. I know T initial for the water is 23.7 degrees Celsius and T final is 27.8 degrees Celsius. I also know the specific heat of water is 4.184, and that is in joules per degree Kelvin. Oh, sorry, joules per gram degree Celsius. All right, I can calculate delta T with my T final minus T initial, and I find that the temperature increased by 4.1 degrees Celsius. All right, so I set up my formula. The energy absorbed by the water is going to be equal to its mass times its specific heat times its delta T. Now, all three of these numbers have to be for H2O. Do not mix in any values that are associated with the metal here. That is a big no-no. All right, if you're going to use the specific heat of water, you got to use its mass and its temperature change. All right, so we've got 100 grams times 4.184 joules per gram degree Celsius times our temperature change of 4.1 degrees Celsius. All right, check our units. Celsius is going to cancel, grams are going to cancel, we'll be left with joules. And we find that water has absorbed 1,715.4 joules. So this is absorbed by our water. All right, now if we want to talk about it from the perspective of the metal, right, it's going to be the same magnitude, so it's still 1,715.4 joules that are moving, but we give it a negative sign to indicate that that energy is being released by our metal. So again, same magnitude, but different sign. All right, so this would be the energy moving. All right, so this is going to be obviously an exothermic process, all right, because energy is transferred from the metal. All right, so that's just one example of how to work a calorimetry problem. Let's slide down to number 2. All right, so this one's going to be a little bit different. It says, what is the final temperature when a 40-gram sample of water at 90 degrees is mixed with a 60-gram sample of water at 25 degrees? This one's a little tricky, all right, because what we basically have are two beakers. All right, we've got beaker A and we've got beaker B. All right, if we look at it in terms of mass, for beaker A, we've got 40 grams of water, and for beaker B, we've got 60 grams of water. All right, we've got an initial temperature for beaker A of 90 degrees Celsius, and we've got an initial temperature for beaker B of 25 degrees Celsius. All right, both of these are going to have the same final temperature, so I'm just going to list it as T final, All right, I know that because the energy will continue to flow until the temperature of both samples are equal to each other. So that numerical value is going to have to be the same. All right, and then our specific heat is also going to be the same, 4.184 for each of these. Oops. All right, the question is, what is that final temperature? All right, so as part of that, I can use my value for Q because I know that Q is going to be equal to specific heat times mass times delta T. And I can get to my final temperature by finding delta T. All right, so if we think about it this way, A is your warmer beaker, right? It's 90 degrees. So the energy is going to flow from A into B. All right, so energy is going to move from A to B, which means that A is going to be a exothermic process, so a negative Q, but that's going to be equal numerically to Q for B. All right. So that lets us use our formulas for Q and set them equal to each other. All right. So it's going to look something like this. All right. Negative the mass of A times the specific heat of water times delta T of A. I'm just going to leave it as delta T for right now. All right. And that's going to be equal to the mass of B times the specific heat of water. Whoops. Sorry about that. Times delta T, but of B. All right, so if I look, specific heat is on both sides of my equal sign, so that's going to cancel. All right, so I can just plug in my values, negative 40 grams for A, and then I'm going to substitute in my numerical values for delta T. So that's going to be T final minus 90 degrees Celsius. All right, on this side, I'm going to put in my mass of B, which is 60 grams, and that's going to be times delta T of B, which is going to be the same, T final minus 25 degrees Celsius, because that was the initial temperature for my B beaker. All right, so you can see I really only have one unknown here, T final. All right, now I'm going to do some distribution, and I get negative 40. I'm going to drop some units here. This is bad practice, but you know. And then I'm going to have plus 3,600. All right, because that negative sign gets distributed as well. And I'll have 60 times T final minus 1,500. All right, then I'm going to do some rearranging. I'm going to move my negative 40 to the right. I'm going to move my negative 1,500 to the left. And what I end up with is 5,100 is equal to 100 times T final. Divide both sides by 100. And my final temperature in both in the beaker when I pour them together is going to be 51 degrees Celsius. All right, so that problem's a little bit different than number one. It's a very creative way to use the formulas because the key here is remembering that the final temperature between the two has got to be the same. So that gives us only one unknown. All right, so now let's slide down to number 3. All right, this one is a more classical type of calorimetry problem, but this one's going to look not at a object in water, but the dissolving, a reaction by dissolving a salt. And we're not looking just for Q, but for the enthalpy change. So this is going to require a little bit of one more extra step. All right, so we're going to have 5 grams of aluminum chloride dissolved in 200 grams of water in a calorimeter. The temperature increases from 25 to 36.8 degrees Celsius. Calculate the delta H for this reaction. All right, now delta H is not the same thing as Q. All right, they are related, all right, but Q looks at the amount of energy flowing for a specific amount of reactant or the specific mass of a substance. Delta H wants you to scale that up to the amount of energy that would flow if you had an entire mole's worth of that substance. All right, so we're going to have to do an extra step. We will need to find Q first, though. That is going to be our first job. All right, so let's start again with our beaker. All right, again, we're going to have water in here. All right, so this is our H2O, and in here we have a mass of 200 grams. We have an initial temperature of 25 degrees Celsius and a final temperature of 36.8 degrees Celsius. And I know the specific heat of water is 4.184 joules grams degree Celsius. All right, again, delta T is the difference between those two, and we find that to be 11.8 degrees Celsius. Now that temperature change occurs because into the water I'm going to drop some aluminum chloride, AlCl3, all right? It has a mass of 5 grams, and it has an initial temperature that is unknown, all right? But the process after it occurs, we reach a final temperature that will be the same as that we saw with water, all right? Now the specific heat, I don't know, all right? But it doesn't matter because I'm going to be using water to determine the amount of energy that's flowing. One thing I do know already is that because the water's temperature increased, that the energy is flowing out from the process into the water. So I know it's an exothermic process. All right, so our first step is to calculate the energy that the water is absorbing. So that's going to be my first step. So I know that Q of the water is going to be equal to its mass times its specific heat times that delta T value. All right, so we're going to have 200 grams times 4.184 for our specific heat times 11.8 degrees Celsius for our temperature change. Plug that into my calculator, and I find that 9,874 joules worth of energy was absorbed by the water while that the aluminum chloride dissolved. All right. Second is to determine, spelling's a lot today, determine the energy of the process. All right, you could also call this energy of reaction. All right, it's a dissolving process, so it's a little hinky about whether that's a reaction or not, but same idea. Just keep in mind that that value is going to be equal in magnitude but opposite in number compared to water. So if water was a positive 9,874 joules and it absorbed that energy, then the dissolving of that aluminum chloride must have been releasing it. So it becomes negative 9,874 joules. So that's going to be released. All right. Now this value is only for this 5 grams. All right, and what delta H, what that enthalpy change is looking at is, well, what if I had, instead of 5 grams, I had a mole's worth of that stuff? All right, so in other words, to calculate that enthalpy change, I actually use a formula. I say that the enthalpy change of that process is equal to the energy that flows because of that process divided by the moles of that reactant, in this case, AlCl3. All right, I know this number, all right, I have it right here, and the moles of AlCl3 I can calculate if I use my grams. All right, so I'm going to come down below and I'm going to say, well, if I have 5 grams of AlCl3, all right, then I can use its molar mass to calculate the moles. So 1 mole of AlCl3 has a molar mass of 133.3 grams. The grams are going to cancel. I plug this into my calculator and I find that I have 0.0375 moles of AlCl3. All right, so to calculate delta H of this process, I'm going to plug in my negative 9,874 joules. That was the amount of energy that was released when I had 5 grams. And I'm going to divide that by the moles that represents. All right, do a division, and I'm going to find that, I have a lot, 263,300 joules per mole are being released. Don't forget your negative sign. You don't get to drop that. All right. Now, that seems like a big number. So usually what you'll see is people put in kilojoules. So they'll divide this number by 1,000 and they would say 263.3 kilojoules per mole. All right. So our unit is going to be this kilojoule per mole, which is also the formula. Q and N. All right. So if you're ever asked to calculate the enthalpy change, just remember you have to do this extra step. You need to figure out the moles of the reactant or substance, and you need to divide Q by that value. And that lets you scale that amount of energy that's flowing up to a full mole's worth. Okay? All right. I hope that was helpful. If you need anything else, let me know.